Hi, welcome to All About Mechanical Engineering. For today's video, the topic of discussion is Reversible Adiabatic Process, or also called as Isentropic process. Now, as per definition of adiabatic process, the process which is carried in such a way that there is no heat interaction between system and surrounding throughout the process is called as adiabatic process. Now, an adiabatic process can be reversible or irreversible. For our case, in today's video, we will consider reversible adiabatic process, which is also called as isentropic process. Now, it should be noted that every adiabatic process cannot be called as isentropic. When the adiabatic process is reversible also, then only it is called as isentropic process. Why is it so? We will understand in this video. So, let's get started. Now, this is the diagrammatic representation of an adiabatic process. We have an insulated system which consists of certain amount of gas in it, and there is a piston. This gas is having increased amount of temperature and pressure right now, and we are allowing it to expand. So, this piston is going to move upward. Let us say this is the final position of our piston having increased volume. So, because of that, you will be having decrease in pressure. So, the diagrammatic representation of a PV diagram is here. We have increased pressure at initial condition and we have decreased pressure at final condition. 1 indicates initial state, 2 indicates final state. As we can see, the pressure reduces and the volume goes on increasing. The same I have shown in this diagram. Now, as discussed in our previous videos, we all know the area under PV curve represents work done. So, if I draw the vertical lines and limit the area, I get this as an area under the PV curve. Means by looking at this picture, we can see for an adiabatic process, work is having a non-zero value. Now, that is another point, whether it is positive or negative. That depends. If it is undergoing an expansion process, you have higher amount of volume final as compared to initial. So, you will be having a positive work output. But if this is getting compressed, then you will be having final value less than initial of the volume, and you will be having more pressure at the final state than initial. So, you will be having work supplied. So, it will be negative. So, whether positive or negative, that will be a non-zero value. So, this is the diagrammatic representation of PV. Now, here on TS chart, we can see initial state 1 is having higher temperature and 2 is having lower temperature. So, there is a change in temperature during the process. For an adiabatic process, there is a change in temperature, but the entropy remains constant. Now, here the entropy remains constant. That's why it is called as isentropic process. But why I am saying that reversible adiabatic process should be called as isentropic, but every adiabatic process is not isentropic. Entropy is a term which depends on two things, that is amount of heat, whether it is added or removed. According to that, the entropy changes, and one more thing is there, that is called as entropy generation. So, for a reversible process, entropy generation is 0. So, if you have a reversible process, generation is 0, so there is no change in entropy because of generation. And at the same time, we are not adding any amount of heat to the system, nor any amount of heat is dissipated from the system. So, heat interaction is 0, and that's why it is adiabatic. And we have a reversible process, so generation is 0, means there is no change in entropy. And that's why reversible adiabatic process is called as isentropic. Whereas, if we have an irreversible adiabatic process, adiabatic means no heat interaction, so heat interaction is 0, but irreversible process will generate certain amount of entropy, means there will be a change in entropy. So, only and only reversible adiabatic process can be called as isentropic, but every adiabatic process is not isentropic. Hope it is clear. Now, applying the first law of thermodynamics to the system. As per first law of thermodynamics applied to a stationary closed system, we have Q equals to delta U plus W. Now for this process we have Q equals to 0. So I can say here 0 equals to delta U plus W, or I can say W equals to minus of delta U. Here putting the value of delta U, I can write minus of U2 minus U1. Taking this minus side inside, I can change the terms and rewrite it U1 minus U2, that is equals to W. Now this equation means if you are getting positive work output from an adiabatic system, adiabatic process, then there will be decrease in internal energy. If this W is positive, equal to indicates this term is also positive, and that is only possible if U1 is greater than U2. This is the first equation, or I can say I can write this in terms of delta U equals to minus W. And that indicates U2 minus U1 equals to minus W. Means in order to increase internal energy of the system for an adiabatic process, work has to be supplied, and that's why it is negative. So in order to increase internal energy during an adiabatic process, you have to supply work. So W will be negative. So these are the terms. Now calculating the W. For any closed system, W is equals to given by integration of 1 to 2 P dV. Now for a adiabatic process, we have an equation PV raised to gamma equals to C. Now as per this, I can write P is nothing but C divided by V raised to gamma. Putting this value of P equals to C divided by V raised to gamma in this equation of W, I can write it is equals to integration 1 to 2 C divided by V raised to gamma into dV. Now C is nothing but a constant, and we can take it out of the integration. So taking it out from the integration, we can write W is equals to C integration of 1 to 2 1 divided by V raised to gamma into dV. Now there is no formula of integration for 1 divided by x raised to y into dx, and that's why I'm writing this by taking this term in numerator. So here it becomes C into integration 1 to 2 into V raised to minus gamma into dV. Taking the integration, I can write W becomes C into bracket V minus gamma plus 1 divided by minus gamma plus 1 from the limit 1 to 2. Now putting the limits, we can say that it becomes a C into bracket V2 minus gamma plus 1 minus V1 minus gamma plus 1 divided by minus gamma plus 1. Now taking C inside and multiplying it and multiplying this equation by minus 1, we get C into V2 minus gamma plus 1 minus C into V1 minus gamma plus 1 divided by minus gamma plus 1, which is equals to, multiplying this and dividing by minus 1, we can write that C V1 minus gamma plus 1 minus C V2 minus gamma plus 1 divided by gamma minus 1. Now what is C? It is nothing but PV raised to gamma equals to C. So we can write it as P1 V1 raised to gamma equals to P2 V2 raised to gamma equals to C. And hence I can put these values in place of C. So putting these values, we get W equals to C P1 V1 raised to gamma, in place of C I have put. Then this term remains V1 raised to minus gamma. We have this base and this as a power. I am separating them, so I can write into V1 minus P2 V2 raised to gamma 4 into V2 raised to minus gamma into V2 divided by gamma minus 1. So here plus gamma minus gamma gets cancelled, plus gamma minus gamma gets cancelled. So W becomes P1 V1 minus P2 V2 divided by gamma minus 1. So this is the amount of work done during an adiabatic process. So this is the value. Now we can also write this in terms of temperature. How? We know that as per ideal gas equation we write PV equals to RT, and that means P1 V1 equals to R into T1 and P2 V2 equals to R into T2. Substituting these values here, W becomes RT1 minus RT2 divided by gamma minus 1, taking out common R T1 minus T2 divided by gamma minus 1. So this is another formula for W. So this is the first formula and this is the second formula. Now there are some relations between pressure, volume and temperature. That relations we'll study in the coming video. Now this was all about an adiabatic process. This is Q equals to 0, W equals to this much, and change in internal energy is equals to W. I hope you have enjoyed this video. For the remaining relationships of adiabatic process, please watch the next video, that is second part of this. Please like and subscribe our channel and stay connected with us. Thank you for watching this video.